Okay, folks, we're going to look at some contextual problems now that deal with quadratic equations. Some may be solvable using factoring. Others, we may have to actually get into quadratic formula again. So let's see what happens when we try some of these. So we're going to try some area problems and some modeling problems. Okay, first one is an area problem. It says a deck of uniform width is to be constructed around a swimming pool that measures 4 meters by 6 meters. Okay, so we have a swimming pool here that's longer side should be 6 meters, shorter side is 4. And if the deck is uniform width, then I guess we can call it X all the way around. Seems to make sense to me. Doesn't matter which corner we pick, we're going to have X and X all the way around this thing. Okay, now it says determine the width of the deck if the total area of the surface of the pool and the deck together is to be 120 square meters. Okay, so let's see. Area is length by width. They told us the area we want is 120 square meters. And the length is going to be 6 plus an extra x that we've added on to either end of it. So 6 plus 2x. And we're going to multiply that by the width, which is 4, with an extra x on either side. So 4 plus 2x. So that gives us 120 is equal to 6 by 4 is 24, plus 6 times 2x is 12x, plus 2x by 4 is 8x, plus 2x by 2x is 4x squared. So 120 is equal to 24 plus 20x plus 4x squared. Now let's see what we can do about putting all this together. We're going to have 4x squared and a 20x over here. Now 24, and I'm going to subtract the 120 to give us a negative 96 on that side. So we've got 0 equals all that stuff. Let's see if we can factor. Well, there's definitely a common factor of 4 there. So we've got 0 equals x squared plus 5x. And then let's see, 96 divided by 4 looks like 24. And let's see if there's two factors of negative 24 that are going to add up to 5. I'd say 3 and 8 are good candidates. Hey, look at that. We got lucky. We got one that factors. So it's going to be x plus 8 and x minus 3. So using zero product property, that tells me that x is plus 8 is going to be 0, or x minus 3 will be 0. Meaning that x is either negative 8, which doesn't make any sense, or x could be 3. I'm going to take 3 to the bank all day long. We got a 3 meter wide deck. It's quite a big deck built around that pool. Okay, let's take a look at the next one. A jumping spider jumps from a low tree branch into the air and lands on the ground. Its height in meters is modeled as a function of time in seconds by this magic equation. When is the spider at a height of 0.75 centimeters? Well, that's pretty simple. We just plug in 0.75 for the height. We've got negative 4.9 t squared plus 0.5t plus 1. Okay, and then to solve this equation, let's get like terms all together. I'm going to put everything on the left side of this equation to make this 4.9t squared business a nice positive number. So I add that to both sides. I have 4.9t squared. And then I've got negative 0.5t. If I subtract that from both sides, so they're both taken care of, I'm going to subtract 1, so 0.75, and then minus 1 is negative 0.25. Looks like to me equals 0. So now we have to solve this, and that looks way too ugly to factor. Let's go quadratic formula. So x is going to be negative b, which will be positive 0.5. Mas or Manos, plus or minus, the square root of b squared. So 0.5 squared is 0.25, whether it's negative or positive. And minus 4 times a times c, so that's 4.9 for a, and negative 0.25 for c. And that's all divided by 2 times a, which is 4.9. Okay, let's simplify this a bit now, and then we'll see what we get for answers. So we have 0.5 plus or minus the square root of, let's see how this works out. Now, I'm thinking that looks a lot harder than it actually is. We got 0.25 here, and what we're actually subtracting is we're going to end up adding because we got a negative and a negative. So we get 4 times a quarter, which is 1 times 4.9. So all we're going to get is 5.15. We put all that together. It's not so bad. All divided by 2 times 4.9, which should be 9.8. Okay, so then we got to take that business and we have to evaluate both the positive possibility and the negative possibility. That doesn't mean positive and negative answers, as we know. It means what happens when we add them and what happens when we subtract them. So let's take a look at that and see what we come up with. All right, so for those, I'm getting, when I add them together, my calculator says I should get 0.282, so about 2.8, and that's going to be in seconds. And if I subtract them, my calculator is saying I should get negative 0.18-ish, and that's going to definitely be extraneous because there's no way we want to have to deal with a negative time. The spider's not jumping back in time, no matter how talented it is. So 0.28 seconds after the spider jumps is when it's at a height of 0.75 meters. Pretty cool spider. All right. So let's remember that when we're solving area problems, we construct a diagram, unless it's given, which often it is, label the dimensions, and include the unknown quantity. It's important to set the equation equal to the correct value, and be careful to model increasing or decreasing areas correctly. The one that we had was one where we actually had a growing rectangle because we built something around the outside of it. That's an increasing area. Sometimes you get decreasing areas. When solving modeling problems, the real key is just to set the function equal to the correct value and solve away. Now, be careful not to confuse the word problems that we do here with the ones we did from the last unit. In this case, we're not looking for the vertex. We're looking for the roots of an equation, so not the vertex. Be very careful. These aren't max-min problems. They're just quadratic equations.